Hi folks, and welcome back to Physics with Captain Rod. The purpose of this video is to describe basically what's called Young's double slit experiment and what it says about light and wave phenomenon. So what we're looking at here, right over on the left, these are representing light wave fronts, not water wave fronts, but light wave fronts. So in optical physics, this light wave front would be approximated with a ray. So I'm going to go ahead and just draw kind of like a ray approximation. So that's what typically a ray means when we use it in physics. The ray is representing these wave fronts of electromagnetic fields moving along, at speed c, 3 × 10⁸ meter per second. All right, what we're looking at here now is a barrier. And this barrier has a pair of openings, one here and one here. And what we're going to do is talk about, all right, what do we expect to see on the right-hand side, or what do we expect to see projected onto this screen? Now, hopefully you've seen my video on diffraction and know that when a wave phenomenon hits a barrier such as this, that what we'll get on the other side here are kind of like spherical wave fronts. So over on the other side, the wave fronts around this barrier are looking something like this. It's going to take me just a moment to sketch these. That's probably enough of those. Now, I have drawn some of the wave fronts around that first barrier. However, there is a second barrier here. And what we're going to get now is a second set of wave fronts. Oops. And important to realize that the wave fronts on the right-hand side also spherical. Now, an important thing to realize is that sometimes these guys are crossing here, right? And then other times they're not, right? And then a peak is crossing, other times it's not. Peak is crossing, other times it's not. So when we look at the right-hand side, and we look at a point in space over here, these two separate wave fronts are not necessarily in the same set of conditions, I guess I'll say for now. They can be, in physics, what we say are out of phase. So over on the right, I'm going to talk a little bit about what do we mean when waves are out of phase and what are the effects of that. So, whoops, don't need that anymore. All right, so here's a wave. And right below it, I'm going to draw another wave. And you'll notice that basically these waves are matching up. So this wave might be going this way or this way. That doesn't matter. Same thing with the one on the right. But just imagine at the instant in time they look like the snapshots I have seen. So hopefully, if you've ever been in a boat or something, and you may have noticed that if you're sitting in a boat and two different waves come by and they hit you at exactly the same time, the boat moves more than it would if either wave went through there individually. That's because when these two waves are right on top of one another like this, we say in physics that they are in phase, and they basically add together. So this would be equivalent to a single wave with a larger amplitude. All right, well, I've drawn better waves. But the idea is this, that when these two waves basically match up, like when this peak is directly in line with this, we would say that these waves are in phase, and they are equivalent to a single wave with basically twice the amplitude if these were equal waves. So when waves are on top of one another and in phase, they add. We call that constructive interference. Right? Now, if I were to take one of these waves and move it over now, maybe to something like this, now they don't add. They interfere with one another. I got to get rid of my old wave here. And now what we would get is something maybe flat. Because, when we add this peak to this trough and so forth everywhere, these waves basically cancel one another out now. And this is called destructive interference. So when two waves are in phase, they add, you get constructive interference. increasing amplitude. When two waves are exactly out of phase like this, you get destructive interference. The resulting single wave, if you think of it as a single wave, has less amplitude. All right, so the same thing's happening over here, where these waveforms are coming together and crossing like this. They're in phase, and the amplitude increases. But in other areas, they're out of phase, so the amplitude decreases. Over on the screen, what we see is a series of bands. We'd see like a bright area where the light is experiencing constructive interference. But if I move up the screen a little bit, we're going to see a darker area where there's destructive interference. And then bright, and then dark, and then bright, and then dark, and then bright, and then dark. Right? So what I'm going to do now is try to attach some mathematics to that. Right? Let's see. So the first thing I'm going to do is I'm going to do this in red. I'm going to put an axis here. Then I'm just going to give a name here. I'm going to call it my principal axis. And I'm going to try to put that right down the center here. And that's going to be the principal axis for this problem. And some important geometries here to consider. Let's see. I'll do green here. These two openings here are separated by some distance here. I'm going to give that a name. All right, so that distance I'm going to call little d here. Now, if I pick a point here, well, let me start with this. This point right here. It's exactly the same distance, right? As long as this is centered, it would be exactly the same distance from this opening to here as this opening to here. So the light would hit here in phase. You know, as I look at my picture and I see that these distances are off slightly, I want to change this. I think I can do that pretty easily. I'm going to go back, yeah, and remodify that. Looks like that principal axis should be down just a little bit. I'm trying to make this picture as accurate as I can. There, that looks a little better centered. All right. So an important point here is the distance from this opening to this point and the distance from this opening to this point on the screen is exactly the same. So we would expect the light to reach that point in phase, the two separate wave sources. Therefore, we would expect a bright spot here. So, right there, whoops, bright in the middle. All right. Now, as we move up the screen, what's happening is this. It's all about what's called the path length. The distance from this opening to this point on the screen here, let's see, do green, right, is that distance. The distance from the second opening to the same point on the screen is this distance. And hopefully, you know, anybody in the class now or anybody watching this video will notice that the second distance that I drew is less than the first distance, right? The difference in distance, right, is right, I'm going to do this in, oh gee, I'm running out of colors here. Let me use this kind of purplish color. That one right there. All the action that we're going to be talking about is about that distance. That's the difference in path length between those two rays, or the difference in path length between this path and this path. Usually most books denote that with the letter delta. You know, the letter delta just generally in math is usually used to represent small distances. If you think about calculus, you know, it's usually an infinitely small distance, but this delta here is the difference in path length. And what's happening now is that when the path length is different, the waves arrive at this point in different phase relationships. So what I'm going to do here, I'm going to draw a little bit, hopefully better waves here. Let me go back and redraw this. All right. So here is a wave. And what I'm going to do is just copy this guy. Oops. Oh, there it is. I guess I got an extra one. My hand was in the way and I didn't see it. Oh, doggone it. There we go. And I did not see that up here. Okay. Okay, there, that should be where there we go. All right, so here's two waves that are in phase. And if they arrived in phase, we would expect constructive interference. Now, as the path length changes, one of the waves basically is shifted. There's a change in phase relationship, and I'm just going to draw it like this. And when these waves are out of phase by this amount, at this point we would have destructive interference. And what would happen is, right here at this point, we would get interference, and it would be dark at that point. Right? So the million-dollar question here is, how far did this wave get shifted over? Now, these waves, remember, have what's called a wavelength to them. The wavelength is the distance between any two successive points. So like from here to here is one wavelength. Or maybe from here to here is one wavelength. And the million-dollar question is, how far did that thing move, did I move that wave over? Okay. And I'm really asking. What do you folks think? Ooh, close. But it's not an angle, it's just a distance. I moved it half of a wavelength. Okay. So at this point right here, we have shifted this wave over by 1/2 wavelength. That's an important thing to understand. At that point right here, they're out of phase by 1/2 of a wavelength. Okay. Now, we're going to actually talk a little bit about, or assign a little bit of math to this now. Remember, the path length difference is this distance I call delta. And I'll draw another distance in this picture. Oops, where did my... Oh, there it is. All right, I'm going to draw this in red. Here is an angle, theta. And it's important to realize from the geometry here that this angle right there would also be theta. Those would be the same angles. And the distance along this path is some distance here. This distance right here, I'm going to call that d. And although it's not a perfect triangle in my picture, but what everyone watching this video needs to focus on is this triangle right here, right there, that has an angle theta in it. The hypotenuse of that triangle is the one I've labeled d. So this distance here, the difference in path length, is equal to delta. That distance I called delta is equal to d sine theta. And now kind of putting these things together. To get destructive interference, this distance, 1/2 wavelength, has to equal the difference in path length, or d sine theta. So I'm going to go ahead and write that equation out. I'm going to write it out in black. So whenever d sine theta, is equal to 1/2 wavelength, we're going to get destructive interference. I don't have room to write all that. Basically, then we get a dark spot. Now, let's kind of imagine this point moves up to here, maybe a little bit further. This waveform would shift further. Now, at that point, these waves are now in phase again. Okay? So the path length difference, the delta here, the purple, is now equal to exactly one wavelength. I'll just put 1 times lambda. And at that point, we get constructive interference, and we get a bright spot. Right? And again, the delta can be written d sine theta. So in this example, if d sine theta is equal to 1/2 wavelength, you get destructive interference and you get a dark area. Okay. As we move up the screen, the path length change here is increasing. And when that path length is equal to 1 wavelength, we get constructive interference and a bright spot. And as you can imagine, as we keep going up the screen, we get a dark spot, bright spot, dark spot, bright spot in both directions. Right? Now, we can kind of generalize this. Let's see. D sine theta equals 1/2 lambda, or 1/2 wavelength. If the path length, if we start at out of phase by lambda over 2, or wavelength over 2, and we go by another path length, another wavelength, we end up out of phase again. So basically, long story short, as we move up this screen, whenever the delta, or the d sine theta, is equal to 1/2 lambda, or 3/2 lambda, or 5/2 lambda, or 7/2 lambda, we're going to end up with dark spots. And whenever it's equal to 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, we're going to end up with bright spots. Right? And this whole apparatus in general is known as Young's double slit experiment. And basically, the mathematics of it is basically this, d sine theta, where d is what's called the slit separation, that distance, equals different multiples, I'll just say different multiples of lambda. This will define where we get bright spots and dark spots. So like 1 lambda bright spot, 2 lambda bright spot, 3 lambda bright spot, and so forth. 1/2 lambda dark spot, 3/2 lambda another dark spot, 5/2 lambda another dark spot, and so forth. Right? So I think I'll stop this video now. It's just meant to be kind of a theoretical video here, and I'll do some examples in the next one. Hope this video helps describe Young's double slit experiment. Have a great day.